Hello my friends, this is Mr. Cozy and this is video 53 where we introduce logarithms. So today I'm going to develop the idea of a logarithm and then we will look at the relationship between logarithms and exponentials. And I guess that's where we need to open, is that logarithms come from exponentials. So let's take a second and look at the graph of f of x equals 2 to the x. Okay? So we're going to make a little sine table here, or not a sine table, a little t-chart. The anchor points that we usually use are -1, 0, and 1 for x. I'm going to add a couple of extras to -2 and 2 just to make things super clear. And we're going to graph these points. We're going to graph them over here. So hit pause, and when you are ready, we'll go. Okay, so let's start at 2. When x is 2, I have 2 to the second, which is 4. When x is 1, I have 2 to the first, which is 2. When x is 0, I have 2 to the 0, which is 1. -1 is it's the same as 1, but it's the reciprocal because it's negative, so it's 1/2. And -2 is 1 over 2 squared, or 1/4. Okay, so plotting these points, I'm going to get 1/4, 1/2, 1, 2, and 4. And if I graph this out, I'm going to get this. Okay? And this is 2 to the x. As we know, 2 to the x has a domain of all reals and a range of 0 to infinity. Okay? Now, the observation that I want to make here is this part of the graph is along an asymptote, which means that it is getting ever closer to 0, but never actually hits it or ever turns away. The gist of what I'm saying is, even though this looks like a flat line, it's actually slowly creeping towards 0, meaning that this graph passes the horizontal line test, even down here, which means that this exponential function, and in fact every exponential function, is 1 to 1. And because it's 1 to 1, it has an inverse. So let's talk about that inverse. Well, if you recall, to make an inverse, you just exchange all of the x and all of the y values. So instead of -2, -1, 0, 1, and 2 as my x's, these are my y values. Excuse me. And all of these y's become x values. And so if I graph these points, 1/4, -2, 1/2, -1, 1, 0, 2, 1, and 4, 2, I get the graph of f inverse. And this inverse has a name which you may have guessed. It is called logarithm. Okay? So this is log of x. Now, I need to be careful here because there's a ton of exponential functions. And the difference between the exponential functions is that their bases are different. So this particular exponential function has 2 as a base. Therefore, its inverse logarithm also has 2 as a base. This is log with 2 as a base of x. Okay, so if this were 3 to the x for some reason, then its inverse would be log with 3 as a base. Okay, the base of the log is the base of whatever exponential the log is the inverse of. Okay, this inverse has a range. I'm sorry, a domain that's the same as the range of 2 to the x, because remember we exchanged x and y to get this inverse. So the domain is 0 to infinity, which we can see from the graph, and the range is all reals. Okay, now this is also 1 to 1, therefore this has an inverse, and as we talked about the other day, the inverse of an inverse is the original function. Okay, so this is where logarithms come from. A logarithm is the inverse of an exponential. Okay, it's what undoes an exponential, and that relationship means that we can convert any exponential to or from a logarithm. And this is how. Suppose we have that y equals some base to the x power. Okay, that is equivalent to saying that the log with the base of y equals x. So this is where the pieces go. The base of the exponent becomes the base of the log. Our exponent becomes the answer, because logarithms are exponents. It's the value of a logarithm is the exponent part of the exponential. And then our answer, our output, when it's an exponential, is our input to the logarithm. It's what we hand to the logarithm to get an answer from. Okay, and with this relationship, we can actually start to compute different logarithms. For the moment, let's just take a second and explore how this works. So I'm going to write some exponential statements. And these are all true exponential statements. There's nothing to solve here. And what I want to do is to convert these to logarithms. So what I do is the base of the exponential is the base of the log. The answer to the exponential is the input. It's what we take the log of. And the exponent is the answer to the logarithm. So hit pause and take a quick stab at this second one here. Okay, I'm doing log 5 as a base. My answer is what I'm taking the log of, and the exponent is the answer of my logarithm. Okay? Now, I can also take logarithms and turn them into exponentials. I can go backwards. The base of the logarithm is the base of the exponential. The answer to the logarithm is my exponent. And what I am taking the log of is the answer to my exponential. Okay, hit pause and take a stab at this second one here. Okay, the base of my log is the base of the exponential. The answer is the exponent, and what I'm taking the log of is the answer to my exponential, 1/16. Okay. Now, where this conversion becomes useful, and we'll talk more about this tomorrow, is this conversion actually helps us to begin to compute simple logarithms. Log with a base of 5 of 125 equals some number. What's that number? I don't know, but I might know it if I convert this logarithm into an exponential. Maybe writing it this way can help me figure out what x is. Or I can start to solve for different parts of a logarithmic equation if I convert this logarithm into an exponential. Oops, equals x. Okay? So converting logs to exponentials can help us solve them. Now, if you want some bonus, take a stab at these two problems and turn them in tomorrow. Okay? All right, I'm a little bit over time, so I'm going to wrap this up here. Have a great day, and I will see you later. Bye-bye.